Welcome to Ask and Learn.
Okay, so for this problem, we are given that Rn represents the number of moves used by the frame-Stewart algorithm. Okay, we want to choose integer k to be the smallest integer such that n, being the number of disks, is less than or equal to k times k plus 1 divided by 2. Okay, and so we want to prove then that R of n, again being the number of moves, is equal to 2 times R of n minus k plus 2 to the k minus 1. And additionally, we want to look at our initial conditions, so that no disks requires no moves, and that having one disk requires one move. Okay, so we start this proof off with the base case, or base step. We'll take where we have 0 disks. So if we have our 4 pegs and no disks on it, we cannot do any moves to solve the puzzle, right? The puzzle is solved just in existence, so R naught is equal to 0. Okay, and then when we have 1 disk, to get that 1 disk to the 4th peg requires 1 move, right? From peg 1 to peg 4. So in the case where we have just 1 disk, it requires 1 move to solve. And so those are the base steps, right? It feels a lot like just solving initial conditions. Okay, then for recurrence, our recurrence step here we consider where we have n disks. Okay, we kind of break it down into 3 broader states, right? So first, we're going to move the n minus k smallest disks. So the smallest disks to the 2nd peg. So if we had our 4 pegs, there's going to be some number of larger disks on one, and then some of these smaller ones on peg 2 left over. Okay, and that's going to require our n minus k moves, right, by the recurrence relation. So next, we want to move the k largest disk, so this is everything that's left on peg 1, to peg 4. Okay, but we have just 3 pegs to work with, where we have to leave that 2nd peg alone in order to get the k largest pegs over to the 4th peg here. Okay, but the Tower of Hanoi uses only 3 pegs, so we can use that Hanoi algorithm to know that it's going to take 2 to the power of k minus 1 moves. Okay, and that was the Hanoi algorithm. Then lastly, so the last thing we want to do here is to move everything that's on that 2nd peg. So we need to move those n minus k smallest disks over to peg 4. Right, to get it on top of the rest of them. So to the 4th peg. And again, we're going to do that in the same amount of moves that we move them to the 2nd peg, namely our n minus k moves. Okay, so Then we just have to sum up these 12 number of moves, right? And so when we do that, we're going to get that R of n is equal to R n minus k. So that was moving the k smallest pegs to that second, smallest disk to the second peg, plus the moves it took to move all the disks from the first peg to the fourth peg. That was 2 to the k minus 1. And plus moving all the disks from the second peg, the k n minus k smallest disks, to the fourth peg. And we have some common terms here, right? So we can combine these two terms to get 2 times r n minus k plus 2 to the k minus 1. And that will complete the proof.